Welcome to the lesson on the importance of electrical fundamentals in motors. In this lesson, we will explore the fundamentals of electricity and its relevance to battery electric vehicles, abbreviated as BEVs. By the end of this lesson, you will be able to explain the importance of electrical fundamentals and how electricity is related to BEVs. Next, you will be able to define and describe the basic structure of an atom. Finally, you will be able to define the key terminologies related to electricity. Understanding the basics of electricity is essential for anyone who uses or works with electrical systems. Electrical fundamentals are important as BEVs rely solely on electricity to operate. The unique nature of BEVs means that knowledge of basic electrical principles is necessary for safe and effective maintenance and repair. BEVs are powered by electric motors, which run on electricity rather than internal combustion engines, abbreviated as ICE. BEVs use electricity stored in batteries to drive the motor and propel the vehicle. Electricity can be hazardous if mishandled. Understanding basic electrical concepts will enable you to work safely around high-voltage systems found in BEVs. While working on BEVs, you must know how to properly isolate power sources, use personal protective equipment, and follow safety protocols to prevent accidents and injuries. Knowledge of electrical fundamentals will also enable you to diagnose and troubleshoot issues effectively. By understanding how electricity flows through the vehicle's systems, you will be able to identify issues such as short circuits, faulty wiring, and malfunctioning components. As BEVs rely on complex electrical systems to power various components such as motors, batteries, inverters, and charging systems, you must comprehend these systems to perform maintenance and repairs efficiently. Though electricity invisibly shapes our world, from powering our appliances to phones and cars, to truly grasp the essence of electricity, we must delve into the foundational unit of all matter, the atom. In this section, we will focus on the atom structure. An atom can be described as the basic building block of matter, which is the stuff that makes up everything around us. Atoms are tiny particles that cannot be seen with the naked eye. Imagine Legos for the universe, but way, way smaller. Atoms come together in specific ways to form all the different materials we see, from a grain of sand to a battery electric vehicle. Electricity revolves around the movement of electrons within atoms. Knowing how these tiny charged particles behave is essential for understanding electrical circuits. Atoms consist of three main components. They are protons, neutrons, and electrons. Let's now look at them in detail. The structure of an atom consists of protons and neutrons surrounded by electrons in orbit around the nucleus. Protons are the positively charged particles that make up part of the nucleus, which is in the center of the atom. Neutrons are the uncharged particles that make up the other part of the nucleus. Electrons are the negatively charged particles that orbit around the nucleus, like the planets orbiting the sun in our solar system. The structure of an atom is related to electricity in two ways: electron movement and electron placement. The movement of electrons from one atom to another creates a flow of electric current. Imagine tiny charged balls, electrons, flowing through a wire like water in a pipe. In electron placement, the number of electrons in an atom's outer shell, also known as the valence shell, determines how well a material conducts electricity by how tightly they are bound together. Metals, for example, have loosely bound outer shell electrons that can move easily, making them good conductors. In contrast, materials like rubber have tightly bound electrons and resist this flow, making them insulators. So, the structure of the atom, particularly the arrangement and behavior of electrons, dictates how electricity interacts with different materials and ultimately creates the flow of current. Imagine the atom like an onion, with layers called electron shells surrounding the nucleus. Each shell holds a specific number of electrons. The outermost shell, called the valence shell, is the most important. This shell is important as it determines the substance's conductivity, insulation properties, or potential as a semiconductor. The number of electrons in the valence shell determines whether a material is a conductor, easily conducts electricity, insulator, resists electricity flow, or semiconductor, acts as both conductor and insulator under certain conditions. Understanding the valence shell is a practical tool to predict how different materials will behave with electricity. An electrical charge is the electrical characteristic of matter caused by its deficiency or excess electrons. This charge disparity manifests intriguing behaviors and interactions in the realm of electricity. Therefore, electrons have a negative charge, while protons in the nucleus have a positive charge. Imagine rubbing a balloon against your hair. As you pull the balloon away, your hair appears to cling to it, displaying an interaction of electrical charges. During this process, the balloon transfers electrons from its valence shell to our hair. Consequently, our hair accumulates an excess of electrons compared to protons, rendering it negatively charged. Having relinquished some electrons, the balloon now possesses a surplus of protons, resulting in a positive charge. In this section, we will focus on some of the basic key terminology to understand electrical fundamentals. The term circuit means circular journey or loop. It is the loop traveled by the electrons. Some essential components must be in a circuit to flow the electrons. Imagine a racetrack for tiny charged particles called electrons. An electric circuit is like a racetrack, but instead of cars, it carries electricity. An electric circuit is a path for transmitting electric current. It includes a device that gives energy to the charged particles constituting the current, such as a battery or a generator, devices that use current, such as lamps, electric motors, or computers, and connecting wires or transmission lines. Electric charge is one of the most fundamental quantities in physics. An electric charge is like a special property of tiny particles within atoms. Think of it as an electrical imbalance. Imagine atoms as little solar systems with a positively charged center and negatively charged electrons orbiting around it. There are three key rules to remember when dealing with charges. First, positive charges repel each other. Second, negative charges repel each other. Third, opposite charges attract each other. Electric current is the rate of the flow of charge. The current in a conductor is measured by the amount of charge, number of electrons, that flows past a certain point in a unit of time. An ampere, or amp, is the unit for current. This is symbolized by the letter A or I. Voltage is defined as the potential difference between 2 points in a circuit. It is used to measure potential difference. It is important to remember that voltage does not flow. It is the pressure that causes the electrons to flow, or the pressure that causes the current. Imagine a water pipe. Voltage is like the water pressure in the pipe. It's not the water itself, current, but the push that forces the water to flow. Resistance, abbreviated as R, is a measure of the opposition to the flow of electric current in an electrical circuit. Resistance is measured in ohms, symbolized by the Greek letter omega. The relationship between voltage and current in an electrical circuit is described by Ohm's law. This law states that the current flowing through a conductor between 2 points is directly proportional to the voltage across the 2 points. Resistance can be compared to the width of the pipe. A pipe with a large diameter will have low resistance compared to a pipe with a small diameter with a high resistance. A watt is the electrical unit for the energy generation or consumption rate. Just like we measure distance in meters or temperature in degrees Celsius, the watt, abbreviated as W, is the standard unit for measuring electrical power. It represents the rate at which electrical energy is used or converted. For example, a high-wattage heater will consume a lot of energy quickly, while low-wattage LED lights use less energy over time. The battery and electrical system need to be able to deliver enough watts to meet the demands of all the components in a BEV. Power is the speed at which electrical energy is used or converted. It's essentially how much work is being done per unit of time. The unit for electrical power is the watt, W. This image depicts how much power different things use. Imagine you have a bunch of light bulbs. A tiny LED light bulb uses only a trickle of power, like a sip of water. That trickle is measured in watts. A toaster uses much more power, like a full glass of water. That amount of power is measured in kilowatts, which is like watts, but bigger. Lots and lots of houses, like a whole neighborhood, use even more power, like a huge swimming pool full of water. That kind of power is measured in megawatts, which is even bigger than kilowatts. The small LED uses just a sip, the toaster uses a glass, and many houses use a whole pool of power. Energy is the ability to do work or cause change. It exists in various forms, like kinetic, motion, potential, stored, thermal, heat, electrical, chemical, nuclear, and more. Energy is measured in joules, abbreviated as J. Joule is the unit of work or energy in the International System of Units, abbreviated as SI. Energy can't be created or destroyed. It can only be converted from one form to another. Think of it like changing shapes with Play-Doh. The total amount stays the same, but the form changes. For example, burning gasoline converts chemical energy to thermal and kinetic energy. Solar panels convert light energy to electrical energy. A conductor is a material whose prominent characteristic is the motion of electric charges leading to the creation of a current flow. Conductors are materials with loosely bound electrons in their outer shells, valence electrons. These loosely bound electrons are free to move around within the material, and an applied voltage can easily set them in motion, creating an electric current. Examples of good conductors include metals like copper, aluminum, gold, and silver. Copper wires are used in BEV battery packs, motors, and throughout the electrical system to carry current. An insulator is a material that blocks or disrupts the flow of electrical or thermal currents. Imagine a water park with slides and a lazy river. An insulator is like a fence around the lazy river, preventing people, electrons, from entering. Common electrical insulators include rubber, plastic, glass, and drywood. Insulators prevent unwanted current flow and protect people from electrical shocks. They also separate electrical components within the BEV to ensure proper functioning. A load refers to any device or component that draws electrical power from a source to perform its intended function, converting electrical energy into another form of energy or output. For example, the primary load in a BEV is converting electrical energy into mechanical energy for propulsion. In alternating current, abbreviated as AC, the direction of the current changes with time. Imagine a wave pattern. AC current goes from zero, increases to a peak in one direction, then decreases back to zero. It then switches direction, reaching another peak in the opposite direction, and finally returns to zero, repeating this cycle continuously. Direct current, abbreviated as DC, is current that always flows in the same direction. Think of DC current like water flowing steadily through a hose in one direction only. There's no back and forth movement, just a constant flow. For example, this is the type of current stored in your phone's battery or a BEV battery. It flows in a single direction, from the positive terminal to the negative terminal. BEV batteries store energy in DC form. A resistor is a component that limits or restricts the flow of current in an electrical circuit. Resistors can be used to limit current, divide voltage, or generate heat. Resistors are like tiny speed bumps in an electrical circuit. They intentionally slow down the flow of electric current, electrons. A capacitor is a device for storing energy as an electrical field. Think of it like a water balloon. You can squeeze a lot of water, electrical energy, into the balloon, capacitor, quickly, but it can't hold much water, energy, for a long time. When you let go of the balloon, the water, energy, rushes out all at once. Let us now recap what we have covered in this lesson on the importance of electrical fundamentals in motors. Electricity is the foundation of how BEVs operate. Understanding electrical fundamentals is essential for the safe and effective maintenance and repair of BEVs. We looked at the basic building block of matter, the atom, and how the movement of electrons within atoms creates electric current. Electrons move from one atom to another, which creates an electric current. We also covered the key terminology related to electricity, such as voltage, current, resistance, watts, and more. Remember, handling electrical systems can be dangerous, and knowing the fundamentals of electricity is essential for ensuring safety while working with or around BEVs and electrical systems. Thank you.